Welcome back to Electromagnetic Spectrum Part 2. In this part, we'll continue our examination of the electromagnetic spectrum.
All electromagnetic radiation is light. Visible light is the only part of the spectrum you can see. For all your life, your eyes have relied on this one narrow band of EM radiation to gather information about your world. Though our sun's visible light appears white, it is really the combined light of the individual rainbow colors with wavelengths ranging from violet at 380 nanometers to red at 700 nanometers. Before Isaac Newton's famed experiment in 1665, people thought that a prism somehow colored the sun's white light as it bent and spread a sunbeam. Newton disproved this idea by using two prisms. To show that white light is made up of the bands of colored light, Newton used a second prism to show that the bands of colored light combine to make white light again. Scientists can learn the composition of an atmosphere by considering how atmospheric particles scatter visible light. Earth's atmosphere, for example, generally looks blue because it contains particles of nitrogen and oxygen, which are just the right size to scatter energy with the wavelength of blue light. When the sun is low in the sky, however, light travels through more of the atmosphere and more blue light is scattered out of the beam of sunlight before it reaches your eyes. Only the longer red and yellow wavelengths are able to pass through, often creating breathtaking sunsets. As objects grow hotter, they radiate energy with a shorter wavelength, changing color before our eyes. Watch a flame shift from yellow to blue as it is adjusted to burn hotter. In the same way, the color of stellar objects tells scientists much about their temperature. Our sun produces more yellow light than any other color because of its surface temperature. If the sun's surface were cooler, say 3000 degrees Celsius, it would look reddish, like the stars Antares and Betelgeuse. If the sun were hotter, say 12,000 degrees Celsius, it would look blue, like the star Rigel. Finally, visible light helps us to explore the far reaches of the universe that humans could not hope to reach physically. Using visible light, the Hubble Space Telescope has created countless images that spark our imagination, inflame our curiosity, and increase our understanding of the universe. Swirling spiral arms of galaxy M33 can be seen in visible light, but the true extent of these spiral arms are revealed in ultraviolet light. Just as a dog can hear a whistle just outside the range of human hearing, bugs can see light just outside the range our eyes can see. A bug zapper emits this ultraviolet light to attract insects. Johann Ritter conducted an experiment in 1801 to find out what, if any, electromagnetic waves are beyond violet. Ritter knew that photographic paper would turn black more rapidly in blue light than in red light, so he tried exposing the paper beyond the violet end of the visible spectrum. Sure enough, the paper turned black, proving the existence of light beyond violet, ultraviolet rays. These ultraviolet rays, or UV radiation, vary in wavelength from 400 nanometers to 10 nanometers and can be subdivided into three regions: UVA, UVB, and UVC. Visible light from the sun passes through the atmosphere and reaches the Earth's surface. UVA, long-wave ultraviolet, is the closest to visible light. Most UVA also reaches the surface, but shorter wavelengths, called UVB, are the harmful rays that cause sunburn. Fortunately, about 95% of these harmful UVB rays are absorbed by ozone in the Earth's atmosphere. Young hot stars shine most of their light beyond the visible light spectrum at ultraviolet wavelengths. Scientists need telescopes in orbit above the Earth's UV-absorbing atmosphere to find and study these UV-bright regions of star formations in distant galaxies. New young stars in the spiral arms of galaxy M81 can be seen in this Galaxy Evolution Explorer GALEX image from NASA. Ultraviolet rays may be harmful to humans, but they are essential to studying the health of our planet's protective atmosphere and give us valuable clues to the formation and composition of distant celestial objects. explodes in a blinding supernova, spraying X-rays across the galaxy to tell its tale. X-rays also tell a dentist which tooth to drill and a surgeon which bones to mend. In 1895, Wilhelm Röntgen discovered that firing streams of X-rays through arms and hands created eerie, but detailed, images of the bones inside. X-rays are high-energy light rays with wavelengths between 3 and 0.03 nanometers, so small that some X-rays are no bigger than many individual atoms. In laboratories, scientists fire beams of X-rays at unknown substances to learn what elements they contain and to decode their atomic structure. This is how scientists unraveled complex molecules like penicillin and DNA. X-rays come from objects that seethe at millions of degrees, such as pulsars, black holes, supernovas, or the plasma in our sun's corona. NASA's SOHO satellite produced these X-ray images of the sun that allow scientists to see and record these energy flows within the corona. NASA's orbiting Chandra X-ray Observatory detects X-rays created by objects spread far across space, such as this supernova explosion that occurred 10,000 light-years from Earth. The colors in the gas and dust cloud correspond to different energy levels of the X-rays created by the blast. X-rays at different wavelengths provide information about an object's composition, temperature, density, or its magnetic field. Human eyes may not be able to see X-rays, but from seething cosmic bodies to individual atomic elements, X-rays provide a wealth of information to exploring scientists. Created by the hottest, most violent, and most energetic objects and events in the universe, gamma rays travel across vast stretches of space, only to be absorbed by Earth's atmosphere. Scientists had no way to detect and study gamma rays from the cosmos until high-altitude balloons and rockets carried gamma-ray sensors above the atmosphere. Deadly to humans, gamma rays are created on Earth by natural radioactive decay, by nuclear explosions, and even by the lightning in thunderstorms. The most energetic of all EM waves, gamma rays carry enough energy to kill living cells. Doctors are able to selectively use gamma radiation to destroy cancer growths. Gamma ray wavelengths are the shortest of all electromagnetic waves, about the size of an atom's nucleus. In fact, it is so short that the rays sail through atoms as easily as comets sail through our solar system. This makes detecting gamma rays difficult for scientists. Gamma rays stream from stars, supernovas, black holes, and pulsars to wash our sky with gamma ray light. NASA's Fermi Gamma Ray Space Telescope imaged the location of these sources, mapping out the Milky Way galaxy by creating a full 360-degree view of the galaxy from our perspective here on Earth. By continuing to study gamma rays, we will unlock important new understanding in astronomy, its use in medical treatments, and allow us to further enhance our protection for our satellites and other electronics here on Earth.
All right, let's recap what we've done. In this video, we defined the electromagnetic spectrum. We took a look at electromagnetic waves and we defined wavelength and frequency. We found out that long wavelength, low frequency waves have low energy, and that short wavelength, high frequency waves have high energy. We looked at some of the uses of the different portions of the electromagnetic spectrum, and we looked at how scientists use the electromagnetic spectrum to explore the universe. If you have any questions regarding this material, please see your teachers. Otherwise, you're ready to move on to the next section. As always, thanks for listening and keep learning.